Okay, so nucleophiles, this will be in an electrophile. Electrophile is sometimes just abbreviated E+. So as I said just in the last thing, so the tail is going to start at the nucleophile, and the point's going to be, the arrowhead is going to be at the electrophile. And remember, for the octet rule must be, you must follow the octet rule. So in the example we just had for HCl, the second arrow, if your nucleophile is grabbing this proton, the second arrow, so this basically follows the tail and point rule. So the nucleophile is a tail, the point's on H. But hydrogen can only have 2 electrons, so it's going to follow the octet rule or the duet rule. And we need to break this bond between hydrogen and chlorine. So whenever we're doing mechanisms, the other type of arrow, which is very common, is when you're breaking a bond, moving to an atom, let's just call it A, and these become lone pairs. And there's lots of examples of this, like both examples we just did. We ended up making chloride, which had 8 valence electrons, happy as can be. Another example would be, and I think we did this example yesterday in class, if you've got, say, CH3, lithium, we've got our carbonyl over here, which has got a delta plus at the bottom carbon. We've got an oxygen, which has got a delta minus. So this bond is polarized. This bond over on the methyl lithium is also polarized. The lithium is the positive side. So we've got carbon, which is delta minus. So if we're doing the mechanism for this reaction, negative is going to go to positive. So carbon with a minus, remember, carbon can't stabilize the negative charge very well. So it's very, very, very reactive. So this arrow, these electrons are going to attack here. And because this carbon has already got 8 electrons, we need to move, we need to break a bond. And we're going to break the pi bond because it is basically the weakest bond. So let's use a red arrow here. So these electrons are going to move up onto the oxygen. And then our final product at this state, oops, it's too low. Let's move this thing over here. Our final product, and let's draw our CH3, and now we've got a negative charge on oxygen. This red arrow is doing exactly what I was talking about over here. So we've got an arrow which is moving up, you're breaking a bond, and it's basically making a lone pair. So whenever there's a mechanism question, if you can identify the nucleophile, this is where the tail of your arrow should be. And if you can identify the electrophile, that's where the point should end up. But if your electrophile is, like if your electrophile is only H+, well, then it's just one arrow. But if it's anything else, there's typically another bond which you need to break. And that, when you're breaking that bond, that is going to become a set of lone pairs. So, and so the bond is going to be the tail. And the pointy end is going to go on the atom. And that's going to end up making that lone pair. I think that, but everyone got the question correct with regard to when we had I- attacking the thing with the chlorine on it. Everyone had that second arrow correct. So the second arrow doesn't seem to be a big problem, but I just thought I'd bring that up just one last time. Okay, any questions on that? Okay, if not, any questions? No. So we started chemical reactivity yesterday, and basically what I'd said was, let me change this. That bond making is going to a lower energy state, and it's going to require energy to make bonds. So that was basically the little start of this. And we talked about enthalpy. You can look up bond strengths on any in any textbook. They'll have a whole series of them. And we did this when we were doing our basically our heat of reaction questions in Gen Chem 1. You might have done more of it in Gen Chem 2, but since I didn't teach Gen Chem 2, that sort of stuff. There's lots of thermodynamics in Gen Chem 2, so I'm sure that you would have seen this before. The key thing to remember, though, is that when these energies are being calculated, they're being calculated to break a bond homolytically. So each section gets 1 electron. And so here was just an example of, this is our radical reaction that we did before, remember? Put chlorine in with isobutane and throw some UV light, boom, you're gonna get this products, and it's gonna be very exothermic. And I ended the lecture with this. If you look at all these bond energies here, what was the thing which looks really odd? And I forgot to write a question about this, and I thought about it like 2 seconds before class started. So what is the thing which is odd in this diagram, or in these bond energies? If I was to say to you, okay. If I was to say to you, which proton is the most acidic, you would say, which proton is the most acidic? A, B, or one of these 3, which are all identical, C. There's lots of people saying to me privately that it's A, right? Somebody said yes. So A is the most acidic, right? So, okay, so then the next question is that if A is the most acidic, if you look at these bond strengths over here, A has actually got the strongest bond. So why would it be easier to break this bond of A? Because that's basically what we're saying. It's easier to break this bond when it's got when it is the strongest bond, according to these bond energies. So A is the strongest bond, but yet it breaks the easiest. What's going on? Anybody want to risk a So what's going on here is that when we're doing, let me go back a slide. So when they're calculating these bond energies, They're actually doing it as if you're breaking the atom homolytically, but, oops, let's see here. But when we're breaking a bond here, how are we breaking it? Are we breaking it homolytically? Or are we breaking it heterolytically? Remember, homolytic, this is basically a radical reaction. And heterolytic, this is basically a polar reaction. Right, so we're breaking it heterolytically. So when they're calculating these bond energies, they're assuming that they're breaking like this. But when we're doing an acid-base reaction, we're relying on the fact that this bond is polarized, and when some base comes to grab this, all of these electrons are going onto the oxygen as opposed to breaking it, instead of being a radical reaction. So yeah, so those tables are interesting. But most of the stuff that we're doing is a polar reaction. So we're breaking them heterolytically. So we're using oxygen's electronegativity to help us break this bond easier than, say, a carbon-hydrogen bond. So with radical reactions, which take place homolytically, an OH bond won't break. We're going to be breaking a carbon-hydrogen bond because they're weaker. But when it comes to, but it's a lot harder to break these bonds in a polar reaction, because carbon and hydrogen, that bond's not polarized. Now, I think someone had a question. Yes, it can cause basically there was a comment that doesn't this cause problems because it doesn't actually reflect true bond strengths, and that's true. It can cause problems, but let me clear some of this mess up here. If you were to this sort of how do I erase this other thing? If you were to go to I know that I fell victim to this myself. If you were to ask grad students in chemistry, so which bond's stronger, an OH bond or a CH bond, almost everyone would say, well, a CH bond's stronger, because they spend their time doing all these polar reactions, and carbon-hydrogen bonds are notoriously not easy to break. So it's just one of those things. But yeah, when it comes to heterolytic bond cleavage, for radical reactions, it's a totally different set of circumstances that are going on. But anyway, it's just an interesting sort of little observation. So these reactions here were all determined, like this is basically all about bond strengths. What delta H basically isn't the ultimate measure of if a reaction is going to take place or not. The real answer lies with entropy, which is commonly called the disorder associated with a system. And so, yeah, like randomness, chaos, disorder, but it really is probably best described as a state of probability. So if you take a coin and you flip that coin, you've got basically a 50-50 chance of getting heads, right? But if you take 4 coins and you flip them all, the chances of getting all heads is now only 1 in 6, because there's more possible states that have something different than just the 4 heads. And so if you've got a system where like you've got a chamber with all bunch of gas molecules in it. It's closed, and you've got a chamber which has got no gas molecules in it. And you open it up. I think intuitively we all think, oh well, gas is of course going to flow into this empty chamber. Like there's a vacuum there, so it's all going to go in there, and it's going to be basically a mixture of the two. Let me get my little laser. It's going to be a mixture of half the gas here and half the gas here. And once we've done this, the probabilities of all of those gas molecules deciding, oh, we're all going to go over here, becomes basically zero, because you've got Avogadro's number of molecules. And if this is the heads chamber and this is the tails chamber, the probability of all the heads being flipped is absolutely zero. There's no chance of that, right? So any process in which is going to generate or increase the entropy is said to be spontaneous. And so basically, when you've got a spontaneous reaction, if you give it enough time, a reaction is going to occur. So I used to say we used to do a little, I used to say to I'd say to this class actually, when we were actually in person, what I would do is I'd say, okay, so if we all take a penny, and I used to hand out a penny and flip it, if everybody gets a heads, I'll give everyone an A of some type, right? And of course I can do that because the chances of a class of 40, everyone flipping a head is so close to zero that it's zero. So, and we'll do a little demonstration of that in a second. So if you've got a diamond will convert to a basically graphite or coal if you give it enough time, because that's actually a spontaneous process. It doesn't mean it's going to happen immediately, because and we'll get to that in a second. But so the real measure if a reaction is going to take place or not deals with entropy. And so let's see here. Right. So this is a simple little test. So I flipped a coin. Did I flip a head or did I flip a tail? And I can't remember what it was off the top of my head because I did this the other day. If anyone can get all 5 of these right, something good will happen, I suppose. Okay, responses. That's interesting. 2/3 of the class, or 3/4 of the class said heads, and the correct answer is heads. Okay, good. Next question. Heads or tails? A little bit more going to tails. Correct answer was heads. All right, so 80% and 67%. Let me write that down. Heads or tails? 1625. So we're shifting to tails, it seems. That's right. 61. All right, a couple more. Start question. $31 on heads, tails 10. Correct answer was tails. 24. Does anyone have all 4 right so far? Okay, we've got at least 2 people. Excellent. 3. All right, so let's do the last one. Do. 27 on heads, 14 on tails. Correct answer was tails, 34. Okay, so we've got a class of basically, there's been, on average, there's been 42 guesses per go. Did anyone get all 5 right? And this is, of course, just a 50-50 sort of 50-50 split. I don't see, let's see here. Okay, we've got quite a few people which seem to have gotten 4 out of 5, but not 5 out of 5. So this is basically, it was just a little silly demonstration to say that, that when the probabilities are really, really, like it's a 50-50 here, when you get past, to get 5 in a row is quite difficult, right? So to get, say, 40 in a row is like, it would be crazy impossible. So it was basically just a demonstration of that. All right, so what was I doing? Okay, so right, now let's do some thermodynamics here, some physical chemistry. So entropy is given the symbol S. And for any reaction, there's a total entropy of there's the system, and then the surroundings. And so the total entropy of these 2 components has to be positive for it to be spontaneous. And so one of the 2 of these, what does this mean? Like the system means what and the surroundings means what? Like those are good questions. Typically the system one's easy to visualize. So if you've got 1 molecule and it breaks into 2, we would say, well, we had 1 and now it's 2. So just the components of the reaction is, started with 1, now we've got 2. We've got 2 things now. That's an increase in disorder or states, right? But that doesn't tell us anything about the surroundings. So the system part here is, okay, that's easy, but it doesn't actually tell us about the rest of it. If you've got a cyclic molecule, so remember when we had our chairs, when we made the chair, we could flip it. So we would move one end down and one end up and vice versa. But that was, and there was a few other ways you could actually twist if you actually built a chair, you could twist it a few things, but the amount of things that you can actually do to that are restricted because it's a cyclic structure. But if you have just a straight chain molecule, and if you think about Newman projections, there's basically an infinite number of rotamers, because you can, let's draw something. If you have a Newman projection, you can rotate this little bond by, you could rotate it by 1 degree, you could rotate it by 2 degrees, you could rotate it by 0.1 degree. So there's basically an infinite number of possibilities of how you draw, like rotate this through any of these bonds, and each bond could actually technically be rotated through. So there's way more possible states in an acyclic molecule than a cyclic molecule. So I guess the point of this little thing here is that with the system, quite often we can say, is it going to a higher amount of disorder just by, okay, am I making 2 possible atoms? Is it going from being a cyclic structure to an acyclic structure? Both of those things are easy to visualize. But the actual surroundings, like this, is really hard to visualize. Yeah, I don't know how to do it. I don't have a good trick of how to do that. So what physical chemists and physicists have done is they basically converted the entropy, the total entropy, into something which is easier to measure and visualize here. So we're not going to go into a whole great deal of physical chemistry, but you might remember that this entropy of the surroundings is equal to the enthalpy of the system divided by heat. I didn't remember that until I read it in a textbook, because physical chemistry is my bane, right? But it's super fascinating. You can learn all sorts of fun stuff with it. But so at constant pressure and temperature, this is basically the surroundings. The thing we couldn't easily visualize can be measured. So this is something we can measure. So they basically manipulated this equation by multiplying by minus temperature to give us entropy total minus entropy total times the temperature. And they give this a new sort of thing called free energy. And there we've got minus T of the system and delta H of the system. And then this gives us our new equation, which is free energy equals the enthalpy of the system, which is something which, and then, oh, sorry, this should be surroundings. Anyway, and minus T of the system, so entropy of the system. Sorry, this is the entropy of the surroundings, because that's what that's been converted to, and this is the entropy of the system. So we've gone from these two things, and now it's nicely packaged as free energy. And they're both measurable. So delta G, now we've got, so for anything to be spontaneous, we want the delta G to be negative. And so we're going to be able to visualize what this looks like in a second. So yeah, all of this math is interesting. So it's taken something which, the entropy total, from something which is easy to visualize and something which is hard to visualize, and converted it into something we can measure in both places, because we can measure the heat of our reaction and we can measure the entropy of the system now through this. So that's all neat. So what we're going to use is what we call energy diagrams. And so certain diagrams that are drawn, like in the case of, let's start a new. So when we had our reaction, UV light, and we made did this radical reaction. Here's our little proton, which is being abstracted. This delta H was negative. So it was an exothermic reaction. It gave off lots of heat. So you might have seen energy diagrams in the past which had delta H here. And the x-axis is what we call the reaction coordinate. Or said another way, so on the left-hand side, this is the start of the reaction. And on the right-hand side, this is the end of the reaction. So it's basically, it could be called time, but it's not really called time. It's just, so in a system like this where it's exothermic, your starting materials would be over here, and your products would be over here. And you are going to go down. So this number here is a negative, this delta H is negative. So this is enthalpy. This is only dealing with heat. It doesn't take into account entropy at all. So let's go back. So with these energy diagrams which have got free energy, this is both the enthalpy and the entropy is included. So we don't say that this is an exothermic or endothermic reaction. We say this is an exergonic reaction or an endergonic reaction. So for a spontaneous reaction, our products are going to be lower and our starting materials are going to be higher. And there's this little hump in the middle here. There's always some sort of activation energy that's required to get this process to go. Sometimes these are very high, sometimes they're lower. For a reaction that's not spontaneous, you would be moving uphill. So there'd be some sort of activation energy and your products would be over here. So free energy, the y-axis should be free energy and not enthalpy. And then the x-axis is what we call the reaction coordinate, which is basically on the left-hand side, this is the start of the reaction, and on the right-hand side, this is the end of the reaction. So these little energy diagrams are a whole lot easier to, like the previous slide, which was manipulating around what is the entropy total versus the entropy of the system or the entropy of the surroundings. We're going to be dealing with energy diagrams as opposed to that type of thing. All right, let's see here. Okay, so there is a question which could be asked. So here's a little example of a reaction, A plus B, and it's in equilibrium with C and D. And so A and B are over here, and there's some activation energy, and C and D are over here. And overall, this is negative. So this reaction is spontaneous, and it's exergonic. So the question could be, shouldn't all of A and B be converted into C and D? Why do we have this? Why isn't this just an arrow like that? Why is it an equilibrium? And so basically the answer to this deals with one of the things that is really hard to visualize for everybody. And that is just the sheer number of molecules that are involved in any reaction. Avogadro's number is enormous. And even if you're not working with a mole of reactants on one side or the other, it's just an incomprehensibly large number. So it's just, the sheer answer is quite often it's impossible to get all it, because for this reaction to take place, A and B have got to collide with one another somehow to make C and D. So equilibria do develop just because of the sheer number of molecules. So in an equilibrium process, we basically have the equilibrium constant. We did this when we were doing acid-base reactions would be 1. We would call that the acid constant. So the products are on top, the reactants are on the bottom. So if this number is larger than this number, then the equilibrium constant will be greater than 1. And the equilibrium is going to favor the products. If K equilibrium is greater than 1, then it's going to favor the products. If K equilibrium is less than 1, so the bottom is a larger number, then it's going to favor the reactants, right? And so you can think of where the equilibrium lies. So what this little graph down here is trying to show is, let me move this so I can see it better, is on the far left, you've got 100% A and B and 0% C and D. And on the right-hand side, this combination would be C and D would be 100% and A and B would be 0. There's going to be a place where the low point in between the two of them, and that's where going to be where the equilibrium is. So this could be 75% C and D, 25% A and B. If the bar was over here, something like this, then the majority of it would be A and B, and this would be a this would be a system where the equilibrium constant favored the reactants. But there is a relationship between free energy and the equilibrium constant, and that's what we're going to get to here in the next stuff. So free energy minus RT ln of the equilibrium constant. And so depending upon where the equilibrium is, the percent products are going to be different. So, and you can just basically plug these things into this equation. So you need, if you notice, if the equilibrium is 1,000, equilibrium constant's 1,000, you're getting to 100% conversion. When it's 100, you're at 99% conversion. And so you notice that this goes up by a factor of 10, and this goes up by a factor of 0.9, right? So, so if you had, when you're getting this even higher, the remaining little bit, you're never quite reaching 100% truly, but in reality, in a practical sense, you're approaching 100%. So, right, so equilibrium do exist because the number of molecules in a system is just so enormous. And there is a relationship between delta G and the equilibrium constant. And you can see that even when it's 10, you're at 90% conversion. It'll be 10% starting material. But once you're getting into this range of like 95%, that's pretty good. So you don't need a large delta G. Anything less than 6, you're getting to a high conversion, right? Anyway, that's why That's why equilibria do exist in a system. It's mainly because there's just so many molecules involved. So delta G is going to tell us if it's negative, is going to tell us if a reaction is spontaneous. So it's going to tell us if it's basically thermodynamically favorable. But it doesn't tell us actually how fast something's going. So, as I said, like the diamond ring turning into graphite is a spontaneous reaction, but that's going to take eons to take place. So you're safe giving a diamond ring to somebody because it's not going to turn into graphite overnight. The study of a reaction rate is what we call kinetics. So kinetics and thermodynamics, the two things which go hand in hand. So a rate of reaction is basically some rate constant, and it's going to be multiplied by the reactant. So the concentration of the reactants. This is going to be important when we're doing substitution reactions and elimination reactions. That'll be the next section. Yeah, I think that's the next section. So how fast a reaction is dependent upon its kinetics. And so when a reaction is taking place, you've got molecule A, and it's going to bump into molecule B. And depending upon the energy that they've got, you could make molecule C. Or maybe they bump into each other and you've still got A and B floating around in your reaction mixture. There's a whole bunch of things which are important to see if this collision is actually going to make C or if it's going to do something else. But yeah, so molecules, they have to collide, but they also have to collide sometimes with the correct sort of orientation. So for example, if you've got pyridine and, oops, get rid of those. Let's say you've got pyridine and you've got HCl, and this bond is polarized in this direction. We've got our Lewis base, which is going to come and grab this proton, and those electrons are going to move on to chlorine. That's all good, but if this comes in and collides with the chlorine side, there's going to be no reaction, because what needs to happen is these lone pairs need to actually hit that proton for the reaction to work, right? So when we draw our mechanisms, we're assuming that everything is approaching things the appropriate way and is colliding the correct way. But that's one of the things that we sort of are missing out on with all of these wonderful little physical chemistry sort of things. So reactions involve collisions, and they have to hit with the correct orientation, have to have the appropriate amount of energy. There's a whole bunch of factors which tend to tell us if the reaction is going to take place or not. But in physical chemistry terms, if the rate of the reaction you can basically add up the exponents here to determine if it's a first order reaction, a second order reaction, or a third order reaction. So if it involves just one of the two substrates, we would say this is a first order reaction. If it involves both, then we would say that this is a second order reaction. And if it involves A squared times the concentration of B, this would be a third order reaction. And you basically determine all of this stuff experimentally. with the stuff we don't really need to get into for what we're doing. But the rate is dependent upon some rate constant and the concentration of the reactants that are involved. Sometimes the rate is dependent upon one of the two, sometimes it's dependent upon both. And the mechanism is going to be important for this sort of stuff. So some reactions only involve one of the two. Some require both. So if you want a reaction to take place faster, the key point here is going to be if you lower the activation energy, the reaction's rate is basically going to increase. So you have your starting materials on the left-hand side, you have your products on the right. And there's some barrier here which you have to overcome for the reaction to take place. And so this barrier, you can think of this as lots of different things. Orientation of the molecule. Does it have enough energy, like enough kinetic energy to when you hit the other molecule for the reaction to actually take place? So for reaction rates, it's dependent upon this activation energy. Now this is sometimes called delta G dagger. So this difference here would be the delta G naught, and this difference here would be the delta G dagger, or the activation energy. So if the delta G naught is negative, it's spontaneous. If the delta G naught is positive, it's not spontaneous or endergonic. It would be uphill. So, but the kinetics, how fast this is, depends upon this little hump here, this activation energy. So how do we decrease this, or how do we give the starting material molecules the energy to overcome this hump? One method is just to provide more energy to the system. So you basically heat stuff up. So when you increase the heat, more of your molecules are going to have the necessary energy to overcome this activation energy. So if you increase the temperature, you often increase the rate. So the what's an example that we can use? Right. So the other day I had an example of this. Something like this. And I drew an arrow like that. And we are going to make two molecules. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. It's going to have a positive charge. Chloride. So we're basically, you take your bottle with the chlorine in it, and you make a carbocation and chloride. So remember, carbocations, these were basically high energy, right? This carbon doesn't want to, it wants a full octet, right? It's electron deficient, right? This is a high energy species. And I said that, you know, we can draw this arrow, and this does happen. You make, so entropy wise, you could say, well, look, you made 2 molecules from one, this is increasing entropy. Great, super, this should, but this doesn't happen just by itself, because on an energy diagram, there is a really high activation energy to get to this point. So if you want to start here and make this carbocation, this is going to be a process where you need to put a lot of energy in, And your carbocation, this guy over here, is going to be right here. This is going to be an androgenic process because this species is high energy because it's missing some lone pairs, for example. But you need to actually heat this guy up to get this to go. It's not going to go if you've got this at room temperature sitting on the shelf. It's not going to happen. So one way to do this is to add temperature to your system to get those molecules over that peak. So that's one way. And that's probably the most common way that we think of is just heat it up. A lot of molecules aren't stable when you increase the heat of stuff. So it's not a universal elixir of making reactions work. Temperature works quite a bit, but it's not the end all or be all. There are steric considerations that are required. So as I was saying before, not only do molecules have to collide with each other, they have to have the appropriate energy and they have to have the appropriate sort of orientation. And often we've got steric factors that can influence the rate of things. So what would be a good example of this? Yes. Okay, so there is one example which I can think of. So earlier today, we had iodine and we had a chlorine atom here, and we did this reaction to make and we drew this. The arrows we used that were the ones that worked were this one and this one. So remember, this was delta plus, this was delta minus, negative goes to plus, and then this arrow here is making our extra lone pair for the chloride. So if we had to classify this reaction, is it a rearrangement? Is it a proton transfer? What was the classification of this type of reaction here, where you're changing the parts? Is it an addition reaction? What was the name for this type of reaction? Right, it was a substitution. So we're exchanging iodine for chlorine, so it's a substitution reaction. Okay, now let's pretend that we've got 3 different molecules here. So, and I'll draw a purple one. Actually, let's erase everything. No, let's not. Let's draw a purple one. One, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so we have got 1 molecule of iodine, iodide, I should say. We've got 1 molecule of this compound, 1 molecule of this compound, and 1 molecule of this compound. So we've got only 4 molecules in our entire reaction mixture. These three chlorines, you will notice they've got the same molecular formula, but different connectivity. So these are a certain type of isomer. What type of yeah, they're a certain type of isomer. What type of isomer would these 3 molecules be? When you've got the same formula, but completely different connectivity. Right, constitutional isomers. Okay, good. So we've got 3 constitutional isomers. Okay, now, so we're doing a substitution reaction. So iodine is attacking this carbon, which has got a delta plus. So over here, let's make this blue, I guess. Delta plus, delta plus. And the chlorine's going to leave after the iodine has attacked that carbon. So of these 3 molecules, which one do you think this iodine would have the easiest, like the difference here? So these are all alkyl halides. But the carbon they're located on is different, right? So this alkyl halide here, this carbon here is bonded to 2 carbons, so it's secondary. This carbon here is bonded to 1 carbon, so it's primary. And this carbon here is bonded to 1, 2, 3 carbons, so it is tertiary. So now, if we go back to the previous slide, we were talking about if things have got steric issues. So if this one molecule has an opportunity to react with one of these 3, which one do you think it would have the easier time reacting with? I've got a lot of responses basically being primary, and that is indeed the case. So if this iodine is going to come in and attack this carbon, or this carbon, in the case of a tertiary, you've got 3 big groups here, which are steric. So if this has got to collide with these molecules with a specific orientation, you've got 3 big groups here that can basically block that. Or you got 2 groups. Here you've only got 1. So we're going to see in the next section that for certain ways that reactions are done, if there's less steric hindrance, the reaction is going to take place faster. So kinetically, it's going to be faster. So here there's less sort of steric interactions around it. So this would react with this primary alkyl halide faster than the other 2. So if there's only 1 molecule of this, it would react with this one, all else being equal. Because when it does collide, you might collide with this one first, but there's all sorts of steric issues with it. So that's what this steric considerations is supposed to be. So you gotta have enough energy to overcome that, but often there's steric factors which will influence the rate. The 4th factor is basically a catalyst. And so what a catalyst does, let's go here. So this is free energy. This is the reaction coordinate, starting materials, products. So this will be delta G naught, and it's negative, so this would be a spontaneous reaction. What a catalyst is going to do is it's going to lower the delta G dagger. So this would be, the green line would be with the catalyst, and the blue line would be without a catalyst. So without a catalyst, you're going to have to put way more energy in to get to the top of this hill to get over. So that's basically, so catalysts can lower that activation energy. And so that's basically another way that you can overcome reduce this. So some ways, like when you increasing the temperature of the system, you're giving more of the starting materials the kinetic energy or the energy to come over this hump. When you add a catalyst, you can keep the temperature lower because they will naturally have more energy to come over that sort of activation energy. Okay. I hope that makes sense. Are there any questions? I'll take that as a no. We've only a couple things. Oh, I guess there's I went too slow. Okay, class is almost over. The thing I'll bring everyone's attention to, I guess we'll have to finish this little section off on Tuesday. But so if in an energy diagram like this, let's say A and B can make two different sets of products. The product which is lower in energy would be what we call the thermodynamic product because it is lower in energy and it is more technically stable. But you could make C and D, and the activation energy to make C and D might be lower than to make E and F. So it's easier to make C and D because the activation energy is, I shouldn't say easier, it's fat. You'd make these two products faster because this activation energy is lower. But C and D would be thermodynamically more stable, but it takes more energy to make those. So there's such a thing as what we call kinetic products and thermodynamic products. Kinetic products, they form faster because they've got a lower activation energy, whereas the thermodynamic products, they've got the delta G, they're lower, so they're thermodynamically more stable. So there is a number of different possibilities where this arises. So you can make a thermodynamic product or a kinetic product. So that's what we would call these things. So as a preview, what we got to do at the end of class, at the end of this, we just need to figure out how to read these diagrams because often there's more than one step in the process. So here you make an intermediate, then you make your final product. So we're going to talk about intermediates, what we call the transition states, and that type of thing. I guess I was a bit slow because basically it's time to probably end class. But we'll just do this, and then after that, the next section is on substitution reactions and elimination reactions. Yep. So that's what we'll do after that. And we'll be using these energy diagrams for those. And we'll very briefly be using some of the kinetic data for that, just to show how to distinguish between the two type of thing. But anyway, thanks for, hope you have a good rest of Thursday. Any questions at all? Alrighty, so have a good day, and I guess I'll see everybody on Tuesday, but stay safe out there in this chaotic world. Okay, and I'll post this lecture on Top Hat at some stage over the next couple of days.
Thank you.
You bet.